Hi, this is Bernard Brault, and this is a follow-up video on a video I made yesterday where I showed how I arrived at the why we have 12 notes, 12 chromatic notes in our scale, in our music, and why it's not an arbitrary number like 10 or 16 or some other number. And there were two basic principles that I used, and the first one was that a note is actually a tone combined with a number of its harmonics. So the harmonics being twice the frequency or 3 times the frequency of that note. And the reason why, when you multiply these notes together, is that we showed that the wave that it forms basically has all of its zero crossing exactly the same as the fundamental frequency. And you could go to the first video and you'll see all of that. So the way I constructed all the sequence of all the notes here, the 12 notes, is by doing the next best thing, which is the next best way to combine two tones is to actually have a fundamental tone and the next one to be a frequency 50% higher or 3/3 higher. And if it's 3/3 higher, it generates a very, very beautiful pattern where alternatively you have zero crossing meeting a peak and the next zero crossing meeting a zero crossing of the second tone. And then again, the video yesterday will show this. And after you sort of iterate this, the 13th time, not after 12 times, the 13th time, you get back very, very close to the same original note. So you started out with a 440 hertz, and then you arrive eventually at the second octave with a note that's, again, very close but not quite. So it's not 440, it's 446. So and if it's twice, so it's not exactly twice the frequency, 880 that you would expect, but it's 892. This left a little bit of a mystery, and at the same time I said I would come back and talk a little bit about this, and that's what I'm going to do here in this video. So now what I'm doing is I'm taking the notes 1 to 12 and I'm just assigning the frequency that we calculated yesterday. So the first one is 440, that's by design. The second one here, 470, comes from the second higher note, which is the B flat right here in the 470. And the third one was a 495, so third note right there. So this is what I did. And when I arrived an octave higher, so here's the first octave. When I arrive an octave higher, I'm going to cheat a little bit. And instead of using the number 892 right here, I'm going to use the same number here, but twice the frequency. Right? Because that's an octave higher. And so this higher up A or A5, if this is A4 and B flat 5 and so on, is twice the frequency of the one below. All right? And if I plot this, frequency versus note, and here's the plot. When you look at the plot, the first note is 440. Here's the second note. So if you were to play all the notes on a chromatic scale and you were to tune your instrument the way I've just described right here, you'd be playing these notes, and this would be the fundamental frequency of all these notes. So this is, and if you look at it, it somehow looks like an exponential. It does look like an exponential, and you would think that maybe, how could we fit an exponential into this, and it might generate a much simpler equation. So that's what I'm going to show you. So here's the next step. I'm going to make this a little bit bigger. So we have here different notes, so the 12th note of the scale, and we have the frequency of each one of the notes, and we know that the first one, the first A4, for example, is going to be 440 hertz, and then it's going to gradually exponentially increase until you hit basically the 12th note or 13 notes higher, and you're going to be on the second octave. And then what we want is this point here to be 880 hertz. And the simplest exponential that you could fit through this looks like this. It's a constant exponential and another constant times the note, right? So we have two unknowns, constant A and constant B, but we have 2 points. We know the value of this point right here, and we know the value of that point. So that should be fairly easy to resolve this equation, and I'm going to show you how we do this. So let's pluck the first point right there into the equation. So we have frequency 440 Hz is equal to A E exponent B times the note, and I'll call this note 0 because it's the beginning of the formula. So E exponent 0 is 1, so immediately what falls out of this is that the A constant's got to be 440. So that's A. Let's take a look at the next point on the graph. So we know that A is 440. Let's plug this point here in the equation and see if we can solve for B now. So the frequency 880 is equals to A is 440, E exponent B 12. So this is this point right there that I plugged into the formula. I move the 440 on the other side, and I isolate the E exponent B12. And this here, 880 divided by 440 is 2, and this is by design because we want the frequency of the 12th note or the octave higher to be twice the frequency. Now we'll do a little bit of a trick. I think if we take the natural log on each side of this, the B times 12 pops out because the natural log cancels out the exponential, and we have the natural log of 2 on the other side. And finally, we just divide both sides by 12, and then we get this value for B. So here's the formula for the frequency of all the notes on the chromatic scale, and it's 440 E exponent this constant here times the note. So let's take this and go back to our Excel spreadsheet and see if we can figure this what the frequencies would be. So I'm going to put the formula in, and it's very simple. So it's if you remember, it's equal to 440 times the exponent of natural log of 2 divided by 12 times the note, which is right here, this minus 1. That should work out. Whoop, little error in the formula. What's EXP right there. Okay. All right, this is live. So I'm just gonna copy down the formula all the way down and see what I get. And so what you'll see here is that we have 440, and of course the next one up here is 880. But notice that all the notes now, so the B flat is no longer 470. It's a little bit off, 466, and the next one is 493.88 and 523. So here's the tuning that we came up with for all the notes and the frequency for all the notes, and this is a tuning that was based on finding out the next best tone, which was 3/2, and figuring out all of its harmonics, versus we came up with this through an exponential function that forced the exponential function to go through 440 here and an octave higher to be twice the value at 880. And what we're finding out is that the value of the frequencies in between is very close to what we had, but not exactly the same. And what's interesting is if you go out on the web and you look for tuning of the notes and the most common tuning, and I'll show you this, and it comes out here. And it says here that A4 is 440. Of course, we knew that. But look at the next one here. So the B flat is 466.16, and we have 466.16376. So all of these numbers that you have here, we just figured them out with this exponential function. It turns out that this tuning method here is called equal temperament, and this is a different tuning. So the equal temperament has one additional property, and the property is that if you were to divide the frequency of all these adjacent notes, so this divided by that is going to be the same as this divided by this. So all the adjacent notes all have the same relative ratio. and this is the reason why we call it equal temperament. And all the ratios are all equal. The advantage of this is that you could start playing a song at any point in time and it will sound exactly the same. And this allows us to transpose song. And this is the reason if you use equal temperament, you can easily transpose. The downside of equal temperament is that all of a sudden the frequencies that we have, if you remember, we came out with the A, and the next, nicest tone that we could combine with the A was E at 660 hertz. And if you remember the reason for that, it was the most fundamental thing where I started yesterday was, the fact that these two tones combine in a way that, alternatively, the zero cross exactly the same point, and then the next time around it crosses at the peak. But when you use equal temperament to tune your instrument, what you'll find is all of a sudden you're slightly off. You're not at 660 anymore, you're 659.25. So this is not going to sound just as nice. It's not going to be as pure. It's not going to be as nice as tuning your instrument to 660. However, the big advantage again is equal temperament, and the fact that you don't need to cheat when you arrive at the next octave higher up. You naturally arrive at at twice the frequency. Versus if you remember, I had to cheat it a little bit on this case. All right, so that's it for this video. I guess we just figured out that there are many different ways of tuning an instrument. We found out one method here that I think probably there's got to be a name for it. I don't know. As I said, I never took music theory before. I'm just sort of figuring this out on my own, and I find it very interesting. And this equal temperament here, that I did search and I did find that, and a way of sorting it out. I will make another video because I did find other interesting things, and these other interesting things go back to where I started, which is combining different tones that basically would combine beautifully and nicely, and I'll make another video on that. All right, thank you very much.